Okay, we want to talk a little bit about work and kinetic energy. Okay, now we haven't defined work and kinetic energy. That's going to come out of what we do here. So the question we ask is what happens if a constant net force is applied to a constant mass through a displacement delta x along the line of the force. I just read that to you, but you focus on the idea that we have a constant net force and a constant mass, and your displacement is along the line of action of the force. So the force is acting in some direction, and the displacement is along the line of action of that force. Could be in the direction of the force or opposite the direction of the force. Okay? And we've experienced that in lab. You know, we have an example of a cart attached by a string to a pulley, and there's a mass down here, and gravitational force accelerates the system. The system, of course, consists of the cart and the mass. The net force is a force of gravity, which accelerates the entire mass of the whole system. Okay? And Newton's second law naturally applies. Okay, that's one just kind of paradigm example. Then we've also observed a ball rolling down an incline. You have the gravitational force, which resolves into components parallel and perpendicular to the axis, and a normal force equal and opposite to this component. And these forces are equal and opposite, so they contribute nothing to the net force. So here's your net force, assuming no friction. And if you got friction, well, you got a little bit of frictional force acting in the opposite direction. Okay? So there's another constant net force as long as this incline is straight. It doesn't look very straight because my hand kind of hit the frame here. But you get the idea, and that's something else we've observed. Or simply, drop something, okay? Or toss something up in the air. Gravity's acting downward. Toss something, projectile, okay? So now, what we're doing here doesn't yet apply to the projectile because the projectile is not moving along the line of the force, okay? The line of the net force. Net force is downward and the projectile's got a path that isn't in the direction of the net force. So we're looking at a special case. And we can generalize this to show that it applies to any case. But let's just get the basic idea. Now, what you know is that that during the interval of displacement, force is constant, so net force is constant. Call this force F net. Call the mass M. Then acceleration is A equals F over F net over M. Okay, you can take my word for it that I wrote the word net there. Remember when I use it. Okay? So now we know that we have some displacement delta x, and we have an expression for the acceleration. Okay? Well, we have an equation of uniformly accelerated motion, which is easily derived from first principles. It tells us that final velocity squared plus initial velocity squared is twice the acceleration times delta x. Well, the acceleration is F net over m, so we have this. Okay? Now, if we multiply both sides by m and divide by 2 and subtract vi squared from both sides before we do that, we get F net delta x equals 1/2 m vf squared minus 1/2 m v pi squared. A simple rearrangement of this equation, and the algebraic rearrangement will give you no trouble at all. Okay? Now, none of this matters. Well, F net delta x is what it is. This applies for any motion, for any starting velocity. If we apply this F net through delta x, the change in the quantity 1/2 mv squared, because that's what this is here, is always going to be the same no matter what the mass is, and no matter what the initial velocity is. Okay, so I'll write delta of 1/2 mv squared for the change in mv squared. And of course the change in mv squared, 1/2 mv squared, is 1/2 m times your final velocity squared minus 1/2 m times your initial velocity squared. In other words, the value you're going to get for 1/2 mv squared minus the value you started with. The later value minus the earlier. That's the change in the value. Okay? So you have this quantity 1/2 mv squared that changes in a way that's always equal to F net delta x. And that's kind of handy. That's kind of an important idea. Newton didn't have that idea, I don't think. At least he never told me about it if he did. But this is, okay, well, we make a definition. We say that F net delta x is work and 1/2 mv squared is what we call kinetic energy. Okay? Now I use a delta W for the work. This is not a conventional notation. And I use KE for kinetic energy. Usually, authors don't put a delta in front of W, and it's kind of inappropriate to do it, but I use the delta in front of W to say that this is a work done on some interval. Okay, this interval is defined by the delta x, the interval in which the force is applied through delta x. So I want to remind us of the fact that this is a work done on some interval. And that's then the change of kinetic energy on the interval. Now, more standard notation, just K, but I'm using KE to remind us what K means. Not everybody is good at remembering what symbols mean. So, okay, so anyhow, that's what this says, okay? So now we've defined work on an interval. It's work done by an F net on the interval. delta x. And KE is what we're going to call kinetic energy. A statement of this law, at least as applied to constant net force, and by integration you can apply it to a variable net force. Okay? This law is called the, or this theorem, okay? We've just proven, at least for constant net force and constant mass, is work done on an interval of displacement is equal to the change in the kinetic energy. Now I could take the statement a little further. The change in the kinetic energy of whatever the work is being done on. Okay? Of the object or system on which the work is being done. And I don't want to get that far with the statement. You can look up various statements of the work kinetic energy theorem. So this is a work kinetic energy theorem. And many authors will call this the work energy theorem. Okay? I like to distinguish this from the version of the theorem that involves potential energy, and I call that the work energy theorem. And that's a language I'll use, and I do that mainly just to distinguish the two and to invoke the relationship between the two. Now, we haven't talked about potential energy. We're just talking about net force and kinetic energy. Okay? So there's your definition. Now, see a little bit about how we can apply this.